Section. Introduction. Since its introduction in 2018, BERT has been a cornerstone of modern natural language processing, NLP. Even with the advent of large language models, LLMs, BERT-style encoder models continue to play a significant role, for instance, in vector database embeddings and retrieval augmented generation in combination with LLMs. Over the past 5 years, there have been numerous advancements in transformer architectures and training configurations that haven't been systematically integrated into BERT. In this research, we demonstrate that these speed optimizations can be successfully applied to the traditional BERT architecture and training process. BERT-style models are usually trained in 2 phases: an initial self-supervised pre-training phase that develops general language representations, and a subsequent supervised fine-tuning phase that uses these representations to tackle a specific task. Historically, the pre-training stage for BERT models has been computationally demanding. For instance, in the original BERT study, the models were trained for 4 full days on 16 Google TPUs. However, in recent years, the time and cost to train BERT models have significantly decreased. A notable study in 2021 managed to reduce the training time of BERT Large to 24 hours on 8 Titan V12 GPUs, and another recent study trained a competitive BERT base model on a single consumer GPU in just 24 hours. In this research, we present our optimized MosaicBERT architecture and demonstrate that certain architectural choices for BERT-style encoders result in a balance between accuracy and time efficiency in pre-training. We do this by empirically comparing MosaicBERT with an optimal BERT baseline that doesn't incorporate our architectural changes but does include non-architectural optimizations such as fast data streaming and optimal floating point precision. We then evaluate these models on the classic GLUE benchmark. Understanding the effects of model architecture modifications and training hyperparameter choices can be challenging when only a few numbers in a table are reported, as is traditionally done in machine learning papers. These numbers can hide differences in the training data, objective function, batch size, training duration, learning rate schedule, and many other details. To show how combinations of architecture choices lead to improvements in both accuracy and training time, we choose to plot accuracy versus training time Pareto curves for all models. Certain architecture changes might increase throughput but decrease accuracy, for example, changes to the floating point precision, while other changes might increase accuracy but take a longer time to converge, for example, increasing the model size. Accuracy versus training time Pareto curves allow us to adequately assess all these changes. The contributions of this work include the implementation of a new BERT-style encoder architecture that optimizes pre-training speed and accuracy. This architecture combines flash attention, alibi, gated linear units, a dynamic unpadding module, and low precision layer norm. We demonstrate that MosaicBERT base achieves an average GLUE dev score of 79.6 in 1.13 hours on 8 180 GB GPS at a cost of roughly $20 on a standard cloud provider. We characterize the accuracy versus pre-training time Pareto frontier for MosaicBERT base and large, and empirically show that the performance of MosaicBERT base and large is Pareto optimal relative to BERT base and large. We also characterize the relative throughput properties of each of MosaicBERT's architecture and design choices via ablations. We characterize the trade-off between model size and training duration, and show that BERT large performance only surpasses BERT base performance after extensive training. We have made our model weights and code publicly available. Lastly, we note that the ideas explored in this study are directly applicable to LLM pre-training, and directly motivated many of the architecture choices around MosaicML's MPT-7B and MPT-30B large language models. To build MosaicBERT, we incorporated architectural choices from the recent transformer literature. These include flash attention, alibi, training with dynamic unpadding, low precision layer norm, and gated linear units. Before describing these modifications in detail, we first review the classic BERT architecture and how we chose a strong baseline. Since our goal here is to show relative improvements in training time and final accuracy, we do not attempt to beat state-of-the-art models for fine-tuning benchmarks such as GLUE. These state-of-the-art models are often trained for much longer and are larger than the models we explore in this study. Section Summary. In this section, the authors introduce MosaicBERT, an optimized BERT-style encoder architecture that improves pre-training speed and accuracy. They incorporate architectural choices from recent transformer literature, such as flash attention, alibi, dynamic unpadding, low precision layer norm, and gated linear units. By comparing MosaicBERT with an optimal BERT baseline, they show that MosaicBERT achieves a high glue score in a significantly shorter training time and at a lower cost. The authors also provide insights into the trade-off between model size and training duration, and they make their model weights and code open source. Section: Choosing a strong BERT baseline. We've chosen a robust BERT model as our starting point. The fundamental building block of BERT models is the transformer block, which is made up of two parts: the attention mechanism and the feed-forward layers. Depending on the model's size, this block is repeated multiple times. For instance, BERT base has 12 transformer blocks, while BERT large has 24. Our baseline BERT base model follows the exact architecture of the original BERT model, which includes a hidden size of 768, an intermediate size of 3072, 12 attention heads, and 12 hidden layers. It also uses the JLU activation function and learned positional embeddings. Similarly, our baseline BERT large model follows the exact architecture of the original BERT large model, which has a hidden size of 1024, an intermediate size of 4096, 16 attention heads, and 24 hidden layers. Our MosaicBERT base and MosaicBERT large models maintain this general structure but introduce modifications to both the attention mechanism and the feed-forward layers. We've made changes to the attention mechanism of MosaicBERT by incorporating flash attention and attention with linear biases, alibi. Flash attention, a recently proposed layer, reduces the number of read-write operations between the GPU's long-term memory, HBM, and short-term memory, SRAM. We've modified the flash attention module to incorporate alibi flexibly. In most BERT models, the positions of tokens in a sequence are encoded using learned position embeddings. Alibi, however, eliminates position embeddings and encodes position information directly through the attention operation. It adds a negative bias to the attention score between each token pair, which grows linearly with the relative distance between the tokens. This biases attention towards nearby tokens and allows for extrapolation to context lengths longer than those used for training. The attention block computes the attention scores between the ITH query and keys, where the head dimension is represented by D and the sequence length by L. Alibi adds a fixed bias with M as a head-specific slope controlling how the bias grows with absolute distance between tokens. The slopes M follow a geometric sequence such that for n heads, each head has a ratio of 2 to the power of -8 divided by n. During fine-tuning or inference, the static bias can be increased to accommodate longer sequence lengths. For instance, a model pre-trained using alibi with a maximum sequence length of 128 tokens can then extrapolate to a task with 256 tokens with little to no decrease in zero-shot performance. This was the original motivation for alibi, which can be considered an indirect speedup method. We've also made modifications to the feed-forward layers of MosaicBERT by using gated linear units, GLU. GLUs incorporate an extra learnable matrix that gates the outputs of the feed-forward layer. We use the JLU, Gaussian error linear unit, activation function with GLU, which is sometimes referred to as JGLU. The GLU module can be described by an equation where X is the input to the feed-forward layer and the matrix V gates the output of the JLU activation function. The extra gating matrix in a GLU model potentially adds additional parameters to a model. We chose to augment our MosaicBERT base model with additional parameters due to GLU modules, as it leads to a Pareto improvement across all timescales. While BERT base has 110 million parameters, MosaicBERT base has 137 million parameters. Despite having more parameters, MosaicBERT base achieves higher accuracy faster than BERT base. Similarly, BERT large has 340 million parameters, and MosaicBERT large has 430 million parameters. Section Summary. The BERT model consists of attention mechanisms and feed-forward layers, with BERT base having 12 transformer blocks and BERT large having 24. MosaicBERT introduces modifications to both the attention mechanism and the feed-forward layers, such as flash attention to reduce memory operations and alibi to encode position information directly through attention. Additionally, MosaicBERT uses gated linear units, GLU, in the feed-forward layers, which improves performance quality. These modifications result in MosaicBERT having more parameters than BERT, but it achieves higher accuracy faster. Section: Additional modifications. We've made some additional modifications to our model, MosaicBERT, to improve its performance. One of these changes involves the use of layer norm, a process that depends on the speed at which data can be transferred from memory to the computing units. Usually, this operation is performed with float32 precision, which requires 4 bytes for each element. However, in MosaicBERT, we've switched to using bfloat16 precision, which only needs 2 bytes per element. This change reduces the amount of data that needs to be transferred, speeding up the process. Although using lower precision can sometimes cause numerical instabilities, we found that this isn't an issue with MosaicBERT. In standard natural language processing, NLP, text samples of varying lengths are combined into a batch and padded with empty tokens to make all sequences the same length. However, this method can lead to wasted operations on the padding tokens. In MosaicBERT, we've taken a different approach by concatenating all examples from a minibatch into a single sequence. This method has been shown to improve training speed as operations aren't performed on padding tokens. We've also made changes to the masked language modeling (MLM) pre-training objective. While the original BERT model used a 15% masking ratio, we found that increasing this to 30% slightly improves accuracy. We've also applied a 0.1 dropout to the feedforward layers but not to the flash attention module, which wasn't possible with the OpenAI Triton implementation. This change also results in a small speed increase. When it comes to pre-training data, we've chosen to train all models on the Colossal Cleaned Common Crawl (C4) corpus, which is a more modern dataset. We've also converted the C4 dataset to the streaming dataset format to ensure that our time measurements aren't affected by data streaming. We've used bfloat16 mixed precision training for all models, which we found to be more stable than using float16 mixed precision. We've also increased the vocab size to be a multiple of 64, which leads to a non-trivial speedup in throughput. For all models, we've used a global batch size of 4096 and a microbatch size of 128. We've set the maximum sequence length during pre-training to 128, and we've used the standard embedding dimension of 768. These hyperparameters were the same for both MosaicBERT and the baseline BERT. In our initial experiments, we pre-trained BERT base and MosaicBERT base for 70,000 steps of batch size 4096, which is approximately 78% of the English C4. We ran experiments with 5 pre-training seeds for each model class. We then fine-tuned these models on the GLUE benchmark suite using identical fine-tuning parameters for all models and experiments. Section Summary. In this section, the authors describe several modifications made to improve the efficiency and performance of MosaicBERT. These modifications include running layer norm modules in bfloat16 precision instead of float32, concatenating all examples from a minibatch into a single sequence to avoid operations on padding tokens, using a 30% masking ratio for pre-training MLM instead of the standard 15%, and applying dropout only to the feedforward layers but not to the flash attention module. They also mention using the Colossal Cleaned Common Crawl (C4) corpus for pre-training, converting the dataset to the streaming dataset format for efficiency, using bfloat16 mixed precision training, increasing the vocab size to be a multiple of 64, and specifying the pre-training hyperparameters. The results show that these modifications led to improved performance in terms of pre-training and downstream tasks. Section. MosaicBERT base achieves 79.6 average GLUE dev score in 1.13 hours. We've achieved an average GLUE dev score of 79.6 with our MosaicBERT base model in just 1.13 hours. This was done using 8 A180GB GPS, costing around $20 on a standard cloud provider. For comparison, the baseline BERT base model achieved an average GLUE dev score of 83.2% in 11.5 hours, while our MosaicBERT model reached the same accuracy in about 4.6 hours on the same hardware. This means our model is about 2.38 times faster. Our MosaicBERT base model consistently outperforms the standard BERT base model in terms of average GLUE accuracy and speed across all training durations. It also outperforms BERT base in 4 out of 8 GLUE tasks. We've found that our model is particularly effective for the largest datasets in the GLUE benchmark, such as MNLI, QNLI, and QQP, which have between 100,000 and 400,000 training examples. However, the performance of both models on smaller datasets is more variable. We also tested our architecture and pre-training choices on a larger model, BERT-large. We found that our MosaicBERT-large model reached an average glue score of 83.2 in 15.85 hours, while BERT-large took 23.35 hours. This means our model is about 1.47 times faster. After 25 hours of training, the average glue score of MosaicBERT-large surpasses that of MosaicBERT-base, reaching an average score of 85.5 in roughly 50 hours. However, MosaicBERT-base is still optimal for a constrained budget and is optimal relative to MosaicBERT-large during the first half of training. We also conducted ablation experiments to determine the best setup for MosaicBERT. We found that low precision layer norm and gated linear units, GLU, affect different parts of the encoder block and therefore work well together. Increasing the masking ratio to 30% slightly improves accuracy without affecting the wall clock time, WCT, while turning off dropout in the attention layer slightly improves both accuracy and WCT. Low precision layer norm significantly speeds up the process, while GLU slows it down but improves accuracy. We also tested MosaicBERT without flash attention and with attention dropout set to 0.1, which is the standard BERT-based configuration. All models were pre-trained on C4 for 70,000 steps with batch size 4096 and microbatch size 256 on 8A 180GB GPS. Section Summary. MosaicBERT-base achieves an average glue score of 79.6 in 1.13 hours, outperforming the baseline BERT-base in terms of both speed and accuracy. MosaicBERT-large, on the other hand, surpasses MosaicBERT-base after 25 hours of training and reaches an average score of 85.5 in roughly 50 hours, indicating that bigger models are not always better. Ablation experiments show that modifications such as low precision layer norm and increasing the masking ratio to 30% provide slight accuracy boosts, while turning off dropout in the attention layer and using gated linear units, GLU, lead to improvements in both accuracy and training time. Section. Related work. In the realm of machine learning, numerous studies have concentrated on a single method or modification that enhances performance, such as flash attention and unpadding. In our research, we've taken a different approach, integrating several of these techniques to see if they work better together. One of the most influential studies in this area is RoBERT, which stands for Robustly Optimized BERT Approach. The researchers behind RoBERT maintained the original BERT architecture but made significant changes to the training process. They removed the next sentence prediction objective, trained the model for a longer period on larger datasets, and altered the batch size, among other things. They discovered that the original BERT was significantly undertrained. For instance, while the original BERT was trained on 16 GB of text, the most accurate version of RoBERT was trained on 160 GB of data for 500,000 steps with a batch size of 8,192. Many of RoBERT's training choices have become standard practice, and our training approach is more similar to RoBERT than to the original BERT. Advancements in transformer architecture and GPU hardware have significantly reduced the cost of pre-training BERT models. A recent paper titled Cramming: Training a Language Model on a Single GPU in One Day is a perfect example of this trend. The researchers aimed to train the best BERT in 24 hours using a single GPU. They modified the BERT architecture to include flash attention and gated linear units, similar to our approach. However, unlike our MosaicBERT, they used scaled sinusoidal positional embeddings and pre-layer norm, and did not alter the pre-training masking rate. Our research shares a similar goal, but we also aim to identify the fastest architecture for pre-training. We provide more detailed insights by demonstrating that MosaicBERT is Pareto optimal relative to BERT. We believe that our training optimization choices for MosaicBERT significantly improve BERT training efficiency. However, there are likely additional modifications that could increase accuracy without affecting throughput, such as replacing layer norm with RMS norm and JGLU with SWI-GLU. A study titled Narrow BERT proposed an ingenious modification to the way encoder blocks are stacked to avoid wasting computation on unmasked tokens. Another recent study demonstrated that dynamically adjusting the masking ratio during pre-training improves BERT's accuracy. However, it's worth noting that not all modifications to the BERT architecture and training process result in improved accuracy. There's also an ongoing debate about the benefits of ROPE, rotary positional embeddings, versus alibi. Other strategies, such as knowledge distillation, might further advance the Pareto frontier of BERT models during pre-training and fine-tuning. One such technique is progressive layer stacking, which involves initializing a larger BERT model with the weights from smaller pre-trained BERT models to speed up pre-training. As the field continues to learn how to optimize stable model training at the billion-parameter scale, we expect some of these innovations to be applied to smaller models like BERT-base. For instance, it's been suggested that adding more layer norm modules at the QK matrix output could improve stability during training. Combining this with a more aggressive learning rate schedule could lead to faster convergence.